Thank you, everyone. It's good to see people again, at least virtually. So my name is William Godoy, part of the Computer Science and Mathematics divisions. My co-authors, you can see Addi and Steve, we're all part of the same division, software engineering group. Today I'm going to talk about extendable, type-safe, thread-safe, asynchronous APIs for our Neutron facilities here. So it's a lot of information, but just think about this is your typical use case of, a facility producing data with HDF5 and see how we can get closer to, the science case. The content from the presentation, I'm gonna, introduce some background slides, some motivation about what Oak Ridge does in terms of neutral facilities. So what are the challenges that I found when I joined this effort? That was last year. What is our proposed long-term solution? That's, what this talk is about. And, the future. We're talking about how, the facility is heavily invested with HDF5. So maybe there are some opportunities to collaborate and see what the future roadmap is. So some background. Oak Ridge Neutron facilities, SNS and HFIR, they fill us with very interesting data. So I encourage the audience to go check this link. And, it's a large investment by DOE, large collaboration, and they're big stakeholders in, HDF5 and the implementation. So all the instruments depicted here, they, produce raw data in HDF5. So it was it's really critical for us to understand what are the challenges and what the users really need and communicate back to the library. So as I mentioned, event-based raw Neutron data is saved to HDF5 files, uses a standard NeXus schema. That's the link actually to the this whole effort of standardizing how this data is stored. It captures a lot of the metadata annotations for each instrument. So typical files have 2,000 to 3,000 entries or more, depending on when they're selling next generation instruments. What's an event? An event is essentially an interaction of the neutrons with a certain type of detector material. You can see here in the picture. I'm not the expert, but my understanding is it's more on the computational side. This data is stored for 3 years, so users can go back and look at it on a cloud-based mode. And production rates are 1.2 terabytes a day. And a grand total of 1.6 petabytes of 2020. So we're not talking necessarily HPC scales, but this is how a lot of the science is done using HDF5. And they use single big nodes for processing. We're not talking parallel nodes or MPI. Mantid, this is the framework I was looking into because it's very popular across Neutron facilities all over the world, and they process this raw event data and turn it into, in-memory workspaces. They have generic loaders. So it's an all-in-one solution for different scientists, different science applications. Typical workflow is typical experimental observational data. You have your raw data. You have some, level 0 data. You introduce some algorithms, data, compute, IO, memory, and then you get the physical quantities of interest. Let me go. So this is an schematic overview. I'm gonna go quickly through this slide. It's just, you have the data producers, raw data is standardized, you have reduced data, and then, model data that the scientists will, that's the understanding of this reduced data that the scientist interprets to, apply to its own applications, to its own science. And this is all accessed remotely, different interfaces. So what are the challenges? This is the current workflows. We saw that there are several glue layers to HDF5. So everybody will come and say, no, my layer is better. I'm actually guilty of doing the same thing in this presentation. So they also have the defunct NeXus API library. It's currently unmaintained. I was telling Elena that I'm part of the committee, so maybe there's some opportunity to revamp that work if facilities agree on something. There is a lot of inefficiencies in data access because this glue layers were built for a specific use case that doesn't really translate to other use cases. Threading opens several, HDF5 descriptors, so we have some lock-in, limitations on the IO. This is well known in the community. And then single files are becoming too large because as you go into the next generation of instruments, they expect to, produce a lot more data. So we apply some short-term improvement. This is the motivation for this slide is, is that not only the data, but also the metadata is important here in the facilities. And we introduce a new in-memory indexing methodology because, if you increase the performance and you reduce facility time, that means, you apply economics. And of course, that turns into a big chunks of money. So the takeaway, these are flame graphs. It's essentially, oh, this is how you've been using HDF5 improperly. And this is the after is how, you can improve that aspect. This is all published and there's some of the impact, is documented here. We get some anywhere from 10% to 30% for the targeted instruments. And the lesson learned is that, hey, we need to do better when it comes to metadata and in-memory indexing at, on the level of top of HDF5. So we propose a long-term solution. And I apologize for the pretentious name. Of course, there's no free lunch. There's always a cost to IO. We're doing some exploratory work here. This is a repository. And the idea is to have, because we know the schemas is standardized, is to have a domain-specific API. So, and try to look for the right levels of abstraction. That depends on the application. And of course, this will be on top of HDF5 without demoting to a, fully domain-specific language approach. So the language will be in terms of, what the scientists understand, NeXus entry bank, or even the backends. So we are tackling two different API levels. The low level is for the performance backends, when you have to load an algorithm and process it. And the high level is mostly like, what the end user will call directly using Python or some, high level language. So we're not there yet. The low level, I think API is already like challenging. So to do that, the first step is to have a pluggable architecture. And, of course, we kind of have to take advantage of all the rich functionality that HDF5 is already producing. And, if there's more like, the ball layer been discussing this meeting or parallel HDF5, if the time and opportunity comes, we have to be open for that. So we kind of implement a virtual transport on top of the virtual transport of HDF5. But the end result is, this quantity of interest that the scientists understand. So a multi-threaded API, what I mean by that is that there's two ways to access the data in a multi-threaded fashion that, we can benefit if we refactor how we access the data. First of all, we want to be type safe, so as close as possible. And I'm going to talk about in a future slides, take advantage of modern C++ for that. And truly threaded if backends allowed. So if there's some opportunity here, if some of the memory operations and HDF5 would allow that in the future, we'll be happy to explore that. So the idea is that two ways of accessing multi-threaded data, right? If you have a big array, each thread will access a single chunk of interest. The other one is more task-based parallelism, like you essentially, it's concurrent execution, you overlap IO and computation. That's what I'm showing here on the right-hand side. So to do that, we kind of thought about what the right APIs are. So first of all, you open a data descriptor, the single shared by descriptor by multiple threads. It builds on top of a single HDF5 file now. Opportunity is that if we have multiple files underneath, we should be able to just access them with a single descriptor. So type safe. What I mean by type safe is that as you are typing, you should be able to replace your strings, which are checked at runtime, at compile time, and even before. I'm going to show that later. So we need safe, we need lazy evaluation, and we are, reference and pointer based because we need to know what the memory, contiguous memory chunks request. We add some convenience APIs if, we need to populate a vector and we don't know the size of the data. So the scientists don't want to really worry about this, and then all the action is essentially passed to the execute instruction, and that could run in the background, and we can, enable overlap. We're not doing anything new revolutionary. We're just looking at, what the IO pattern is and see if we can come up with APIs that allow this. And then, you know, after you call the future back, then your data should be available when you need it. Similarly, the single instruction, multiple data. So just think of C++ threads or OpenMP or, you know, or P threads, your favorite thread implementation. So you implement any callable that each thread is going to call accordingly. So each thread ID will request a piece of that array. This is for large arrays, obviously. So why? Because a lot of the compute algorithms are designed this way. So you essentially, once again, open your thread safe handler, you launch your threads, each thread will take a single view of, you know, your data, and then there's opportunity for parallelization, like for example, those binary tree searches, if they can be done, you know, in a concurrent way. Then you join your threads and then boom, your data is available as you need it. Now, what I mean by type safety, there is a very nice paper, actually, Soren is one of the co-authors, in which, you know, we know this is not a standardized thing, that each problem and the way you process it, the metadata, you know, will require a different type of metadata other than what you have and layout in HDF5, which follows a typical file system, right? So the nice implementation we have with C++, this is only possible with C++ 17, is that you can actually have a more natural way to express that relationship between the metadata you need in index and the one you retrieve from your descriptor. So this is extendable. So one day you will need a hash, one day you need, you know, a binary tree, you name it. It depends on what you want to do with that data. In that previous paper, for example, I have this smaller one. That's the one we needed for the NeXus API, but we should be able to extend those things on top of HDF5. Similarly, not only the metadata, but the data entries, ideally being type safe, you know, will allow to catch errors before runtime. It would also enable, you know, users, because remember, we have 2,000, 3,000 entries to remember. They don't have to remember all this. Your favorite editor will be able to retrieve this, as you know, because there's a lot of things to remember when it comes to the annotation stored in the NeXus file. So this is only, again, possible with C++ auto template deductions. So, you know, we got good feedback about this approach, and it's extendable. It's not particular to one data schema or model, but it maps nicely the hierarchical nature of HDF5 entries. So in summary, we're kind of trying to tackle array-based data as well as in-memory metadata index, because that's also one of the biggest bottlenecks we have. And that's essential for the reduction workflows that we found here at Oak Ridge. So current data access implementations are, you know, very application specific. They're one-off, and they mostly, for the most part, map one-to-one the HDF5 API call. So they don't really add much value other than, oh, this is my wrapper. So we are trying to add some value by presenting something that's extendable to other applications, because it's our very generic concepts. You know, and right now this is still exploratory, but we're running regression without actual NeXus data. Here, the future. I wish I had the answer to this, but nobody really knows, because what we know for sure is that more data is going to be produced. We have the second target stations, the next generation of instruments, and they're still going to use HDF5, of course. We're talking earlier with Elena, like, are we ready to this convergence between the HPC world and, you know, what experimental facilities need, you know, because there's so much knowledge that can be translated to this area. We're still thinking about extension to high-level languages, because, you know, they have their own challenges. You know, can we extend this compile time safety to just in time? You know, we also have the global interpreted log for threaded APIs. Julia is an interesting language, because even though it's a script, it's trying to close the gap between, you know, a scripted language and performance. So there's a lot of things to understand. And some of these ideas, of course, they need operational patron support. You know, it's up to the facilities, because quality software, as you know very well, is a large investment. It's much larger than we as researchers can come up with and, you know, try to understand at an operational level. So I want to acknowledge our sponsors, the Office of Basic Energy Sciences, the DOE. I want to thank the organizers and HDF5 groups and all the HDF5 stakeholders. And thanks to the audience ready for questions.
Thank you so much, Willem. We have some time for questions.
Mm-hmm.
So let me start with some naive questions. Like in the multi-threading you're talking about, is that multi-threading within a node, multiple threads trying to write or read data?
That's correct for them. So that's a good question, actually. For the most part, they try to read because the data is already stored. Yes. The write so it's typical, like you write once and you read many times. That's kind of the pattern. So there's still a need for write APIs. In the GitHub repo that I'm sharing, of course, to do all the testing and all that, I need a writer, right? So like, I can make sure my reader works. So yes, there is definitely, it's the same pattern. You write, each thread will write a chunk of data, and then the readers will kind of, you know, access it maybe in a different proportion, but still needed.
Okay. And how parallel are these applications? I mean, do they also do the multi-process based parallelism or just the multi-thread?
Absolutely. So so we use Intel Xeon, you know, like many cores, you know, I think these are like 64. So some of the, because this is experimental data, they run, it's ensemble based. So they run several times, you know, the same experiment, changing parameters. So a lot of this can be independently analyzed, like they retrieve that. So it's a perfect scenario for threaded IO, unless they need some collective operation, right? So in that sense, it's not very different from the HPC we know. So we use multi-threads, not MPI.
Any others have questions? If not, I can ask one more. Okay, so the other question is related to sparsity. Many of the experimental observational data sets are sparse. So how is sparsity managed in your case? Are you doing anything special about it at all, or is just going dense arrays?
You know, that's a very, very good question, because the way the instruments are outlined, they're detectors, right? And you know, take it with a grain of salt, because I'm not an expert in that domain. But they store what they call the time of flight per pixel. So it's essentially a sample of, you know, how many neutrons actually impacted a certain pixel or certain detector. So the application itself is not as complex as, you know, those type of experimental observational you're describing, in the sense that they can calibrate the instruments, and they just end up with a nice 1D array or 2D array of time of flights, and they discard what they don't need, or they just replace those as you know, zeros. Or there, in fact, Mantid has a filter for not a number kind of stuff, but you know, under the hood we can treat it as, you know, zeros, you know. So they're not, it's not that complex in that regard, but that's a very good question.
Okay, cool. All right. Cool. There are no other questions. Thank you, William, again.
Good seeing you again, everyone. Thank you.